Welcome back, everybody. This is going to be Lecture 8. We normally do this right after we did Exam 1, so in the summertime we don't have time to just simply devote an entire day to an exam. So we would normally do the first half of the class period as an exam, and then the second half of the class we'd go ahead and continue on with an actual lecture. It's not ideal, but it's what we have to do in the summer. So, this is going to be Chapter 8. We're going to start talking about Chapter 4. That's going to be our goal here. Chapter 4, in the Changle and Bowles text, I always like to say Chapter 4 is kind of like a first law for closed systems. My hope is you remember what a closed system is. Okay. Again, this is Chapter 4 in the Changle and Bowles text. This is going to be Lecture 8. This is page 1. Okay, so our goal here, Chapter 4 being first law for closed systems, as we said, and so we'll reintroduce the first law and explore some simplifications for first law for closed stationary systems. So if we look at, let's just move this out of my way here. Again, if we reintroduce the first law, recall that this is the idea that the total rate of energy in minus the total rate of energy out of our system is going to equal dE dt for our system, the change in the energy for our system with respect to time. Now, what we're going to do for most of our situations, we're going to say, well, let's not worry about every little tiny change in the energy of our system over every little differential slice of time. Let's just be concerned with a total change in the energy for our system over a total period of time. Okay, and again, I'm not expecting you to have had differential equations at this point, and even if you have, you only kind of probably only have some rudimentary tools to try to tackle or challenge this expression. One of those that we're going to employ is basically we're going to assume this is a separable equation. Again, if you've not had differentials, that's okay. Those of you that have had, we're basically going to assume this is a separable differential equation. We're going to say, well, just take the total amount of time, multiply by the total rate in minus the total rate out. And we're going to set that equal to the total energy change for our system. Now, what happens if I take rate times time? Well, if we're talking about speed, speed is a distance rate. So if I multiply distance rate by time, I get distance. Right? So multiply speed by time, I get distance. Same thing here. If I take an energy rate, that's what the dot tells us. This is measured per unit time. So energy per unit time multiplied by time just leaves me with energy. So the total energy out in minus the total energy out equals the total energy change for our system. Now, what we can do is say, well, what are the ways that energy can cross our boundary? What are the ways that energy can come into or out of our system? Well, if it's a closed system, because there's no mass crossing the boundary, again, I said I want you to know what that means. Closed system means there's no mass crossing the boundary. The only way energy can come across is in the form of heat and work. And those same quantities can go out. And again, you can rearrange and write these in any order, these first four terms, as long as you preserve the sign. Then if we think about what is the type of energy that can change for our system, well, again, mass being constant, so I'm going to factor that out. And then I can have what we call the internal energy, kind of the molecular thermal energy. We can have kinetic energy of our system. We talked about in the Physics 1 class. We introduced this or mentioned this again in Chapter 2. And then we could have potential energy based on the distance from the center of the Earth. Now, what we will often do, so this would be first law, let's add this out here, first law for closed stationary systems. All right, so this is first law for closed systems, what I have here. This is first law for closed systems. Now if I say first law for closed stationary, adding a second adjective here, adding stationary to systems as well. So closed and stationary systems, two adjectives there. That's adding an additional assumption. Now what happens is if I add additional assumptions, I can normally simplify the expression. Now I can still have heat and work crossing the boundary, both in the in and out direction. So I just need to add the ins, subtract the outs, okay? And that's going to equal then, if it's stationary, what is that telling us? I'm hoping you're yelling at your screen and everybody around you thinks you're crazy. You're yelling at your screen, it's not moving, right? Stationary means it's not moving. You're right, so if it's not moving, what energies do not change? And again, giving a nice little show for anybody sitting around you. Yeah, you're right, the kinetic energy and the potential energies do not change. So the only energy that's going to change is the internal energy. This is the most common form of the first law that we're going to use in Chapter 4. In Chapter 4, we will often be dealing with closed stationary systems. In Chapter 2, we're just kind of introducing the first law, reintroducing conservation of energy, including the thermal energies. Now we're saying, well, this is the first law if we ignore changes in kinetic and potential energy, because they're either going to be zero or negligible. This is the primary form of the first law we'll use for closed stationary systems. Okay? So, again, as I add assumptions, as I add simplifications, if you will, the equation gets more simple. So when you see a simple, easy-to-use equation, you need to make sure you understand, I need to know what assumptions were used to come to this derivation. Because to get from this differential equation up here down to something that we can use with just some algebra, some assumptions had to be made. I had to assume that I don't really care about every little differential slice of time. I just need to know the total change over the total time. And then, on top of that, I need to assume that it's closed and stationary. Then I get down to this simple equation. Again, when you see a simple equation in our line of work as engineers, when you see a simple equation, alarm bells need to go off of, I need to know what are the assumptions associated with that equation before I try to use it. If not, you design something, it doesn't work, potentially breaks, potentially causes harm or death, that's kind of on you. That's kind of a big deal. So, again, simple equation means there's assumptions. Make sure you know the assumptions needed to use it. I don't expect you to do the derivation personally, but I do expect you, once the derivation's done, to know how you got there and what rules you have to follow to use it. Okay, get off my soapbox here. Let's continue on. Now, if we let's do a couple of things here. If we let a quantity we call Q net in, right, basically the total heat into the system, and we say that's equal to the heat in minus the heat out, and we let a quantity we call W net out equal W out minus W in. Then I can rewrite this equation here. I can say, and I'm sorry, this is W out up here. Right? So if we rewrite this equation saying, well, if I take the work out minus the work in, seriously? Let's just rewrite this thing. I apologize. I've just noticed all my subscripts are messed up. I was trying to talk and write at the same time, and sometimes that works, sometimes it doesn't. Work in plus heat in minus work out minus heat out is equal to M delta U. So instead of yelling at your screen about stationary. You were yelling at me about, hey Steve, your subscripts are wrong. I apologize. Add the energies in, subtract the energies out. Okay, this is the way your text suggests we do this. Do the first law. This is not common in all texts. In fact, if you're joining me from another class and you're learning out of another text, they are probably going to say, well, they're probably going to use this idea that Q net in minus W net out, which of course is equal to, in our nomenclature, that is Qn minus Q out minus W out minus Wn, right, here, right? If that's the case, then that's equal to M delta U. Right? So what you'll find is in some texts, this is how they'll introduce the first law. They'll say, well, Q minus W is equal to U. And you'll see that in a lot of texts. They'll say Q minus W is equal to U. What they're saying there, they're saying that the Q net in minus the W net out is equal to M delta U. And again, in our nomenclature, we say, well, what we're actually saying is add the energy that comes in, subtract the energy that goes out, and that's equal to the change. Right? Our preference is to say add the ins, subtract the outs, that equals the change. This is the way a lot of texts will teach you. Say, well, add the heat, subtract the work, that equals the change in U. They're making the assumption there that work in the out direction is positive and heat in the in direction is positive. So again, this is a further simplification of this expression. Right? So we can take this differential equation and simplify it all the way down here as long as you remember the rules associated with this version. The rules here are this is a closed stationary system, and you have to remember that this represents Qn minus Q out, and this represents work out minus work in. Now, if you want to remember all of that and write the expression this way, that's fine with me. It doesn't bother me. This is how I will try to approach it, because this is how your text will approach it in chapters 4 and 5. Chapters 7, 6, and beyond, they'll kind of revert back to this form a lot more. This is kind of the traditional form of the first law. Steve, why in the world would we use that? Well, here's the truth. The science of thermodynamics was the idea of we want to put heat into this device and get work out of it. So those are the quantities we wanted. We wanted to put heat in. We didn't want to lose heat out, so that was negative. Heat out would be negative. Heat in is positive. And we wanted to get work out, so that was the positive quantity. To put work in was a negative. That was not what we wanted to do. So work in was the negative quantity. And that's the reason for that sign convention. Again, it's still prevalent in some text, but this is how our text likes to present it. Add the ins, subtract the outs. Now my alarm's about to go off here. Thank you. Let me look at my time, because I restarted the video, so I've got about a minute here before I quit. But I'm thinking that might actually be, you know what, I'm going to stop there. That's actually not a bad place to stop, and we'll pick up on the next video.